Okay, ma'am. A very good morning, everyone. National Mathematics Day falls every year on 22nd December to recognize and honor the work of one of the greatest Indian mathematicians, Srinivasa Ramanujan. Srinivasa Ramanujan Iyengar was born on 22nd December 1887 in Erode, Madras. His father worked as a clerk in a sari shop and mother was a housewife. A child prodigy, by age 11, he had exhausted the mathematical knowledge of two college students who were lodgers at his home. In 1910, after meeting the 23-year-old Ramanujan, the founder of the Indian Mathematical Society, V. Ramaswamy Iyer, sent Ramanujan with letters of introduction to his mathematician friends in Madras. Though he had no formal training in pure mathematics, he made substantial contributions to mathematical analysis, number theory, infinite series, and continued fractions, including solution to mathematical problems then considered unsolvable. Seeking mathematicians who could better understand his work, in 1913 he began a postal correspondence with the English mathematician G.H. Hardy at the University of Cambridge, England. Recognizing Ramanujan's work as extraordinary, Hardy arranged for him to travel to Cambridge. In his notes, Hardy commented that Ramanujan had produced groundbreaking new theorems. During his short life, Ramanujan's results, many were completely novel and highly unconventional results, such as the Ramanujan prime, the Ramanujan theta function, partition formulae, and mock theta functions, and they have opened entire new areas of work and inspired a vast amount of further research. He became one of the youngest fellows of the Royal Society and the first Indian to be elected as a fellow of Trinity College, Cambridge. Of his original letters, Hardy stated that a single look was enough to show that they have been written only by a mathematician of the highest caliber, comparing Ramanujan to mathematical geniuses such as Euler and Jacobi. In 1919, ill health compelled Ramanujan's return to India, where he died on 6th April 1920 at the age of 32. A deeply religious Ramanujan credited his substantial mathematical capacities to divinity and once said that an equation for me has no meaning unless it expresses a thought of God. The former Honorable Prime Minister of India, Dr. Manmohan Singh, declared 22nd December as National Mathematics Day on 26 February 2012 at Madras University, remembering his achievements and contributions. Henceforth, National Mathematics Day is celebrated in each year in India on 22nd December to mark the birth anniversary of the legendary Indian mathematician Srinivasa Ramanujan. Dr. Manmohan Singh, on the occasion of National Mathematics Day, said, "A genius like Ramanujan would shine bright even in the most adverse of circumstances, but we should be geared to encourage and nurture good talent." Ramanujan. His indelible contribution to mathematical analysis, number theory, infinite series, and continued fractions will always inspire the mathematicians. Mathematics is the biggest motivation because it starts with zero and goes up to infinity. So let us celebrate National Mathematics Day by keeping aside all the fears for mathematics and embracing this subject with love. It is my pleasure to welcome you all for this 2 days program on National Mathematics Day, sponsored by Haryana State Council for Science, Innovation and Technology to commemorate the birth anniversary of Srinivasa Ramanujan. I, Dr. Manu Rohila and Dr. Meenu Chawla, on behalf of the Department of Mathematics, J.C. Bose University of Science and Technology, YMCA Faridabad, extend a very warm welcome to all of you. It is our privilege that we have amongst us today our worthy Registrar Sir, Dr. Sunil Kumar Garg, who has always taken a keen personal interest in every aspect of this university. On behalf of the department and on my own, I welcome you, sir, with greatest reverence and highest admiration. It is my pleasure to welcome all the eminent speakers, faculty members of the department, and participants present here today. It is our holy tradition to worship our goddess Saraswati before any important event. It is believed that goddess Saraswati endows human beings with the powers of speech, wisdom, and learning. In order to bestow our purest prayer in her feet, I invite you all to join us for Ma Saraswati Vandana. Now, I request Professor Neetu Gupta, Chairperson, Department of Mathematics, to give a brief introduction about this 2 days program on National Mathematics Day. Due to some technical error, ma'am is joining in just 2 minutes. Please, sorry for this delay. There is some technical error. Ma'am is joining in just 2 minutes.
Okay, good morning, everyone. Worthy Registrar Sir, Professor Sunil Kumar Garg, Professor H.C. Taneja, Department of Applied Mathematics, Delhi Technological University, Delhi, all my colleagues and dear students. On behalf of Department of Mathematics, I extend a warm welcome to all of you in this program. This program is being sponsored by Haryana State Council of Science, Innovation and Technology. It's a matter of great pleasure for us that Professor H.C. Taneja is here to grace the program. Thank you very much, sir, for giving us your valuable time. I would like to express my gratitude to our Honorable Vice Chancellor, sir, and Registrar, sir, who gave permission and motivation to organize this program. On the occasion of 134th birth anniversary of a genius and a self-taught mathematician, Srinivasa Ramanujan, the Department of Mathematics is celebrating the National Mathematics Day. Nothing can be more apt than to remember this genius through the celebration of Mathematics Day. The talent and work of Ramanujan are appreciated and followed across the globe to this date. Mathematics, the base of all things around us, is celebrated and its greatness is observed yet again on this special day. The main objective behind this celebration is to raise awareness among people about the importance of mathematics for the development of humanity. Several initiatives are taken to motivate, enthuse, and inculcate a positive attitude towards learning mathematics among the younger generation of the country. Mathematics helps us understand the world and provide an effective way of building mental discipline. I think it is impossible to limit the uses of mathematics in everyday life. The importance of mathematics is that it is a method based on research and analysis to reach the desired results and is used for calculation and presentation of data whose use is not limited in a particular field, but in all the areas of life and different sciences. Under this celebration, we have organized various competitions for the students. Yesterday, we have organized national level debate competition, poster making competition, PowerPoint presentation competition, and today also there is a national level Rangoli competition in offline mode. Today, we have with us two eminent speakers. First one, Professor H.C. Taneja, Department of Applied Mathematics, Delhi Technological University, Delhi. He will deliver a lecture on application of mathematics. Second one is Professor Pankaj Gupta, Department of Operational Research, University of Delhi, Delhi. Their expertise will really surely benefit the students as well as the faculty members. In the end, once again, I welcome Professor H.C. Taneja, Registrar Sir, for sparing his valuable time. I also congratulate all the faculty members of Department of Mathematics for organizing this wonderful program. Thank you.
Thank you, ma'am.
Thank you, ma'am, for giving the insights of the workshop. We are delighted to have the gracious presence of our worthy registrar, Dr. Sunil Kumar Garg, sir. Sir has a vast experience in academia, research and development, industries, and administration.
Please,
spread over
can we continue further?
Sir has 24 research publications to his credit in national and international journals.
Can we continue?
Sir has served many academic and technical institutions. Dr. Sunil
sir
is the founder member of the Indian Society of Surface Science and Technology. He is a life member of Indian Society of Analytical Scientists and Indian Society of Technical Education. I warmly welcome our worthy registrar, sir, who has been a source of encouragement and support to us in all our endeavors. His invaluable guidance is always cherished by all of us. I request Dr. Sunil Kumar Garg, sir, to share his vision with us and formally welcome our today's experts. We look forward for your advice and direction, sir.
Thank you, Dr. Manu. I hope I am audible. I am audible?
Yes, sir, you are audible, sir.
Okay. First of all, a very warm good morning to all of you who are present here. I welcome our today's expert, Professor S.C. Taneja ji from Department of Applied Mathematics, Delhi Technological University, Delhi, and Professor Pankaj Gupta, Department of Operational Research from University of Delhi. As you know, our country has very glorious history of mathematics, and today is 131 birth anniversary of legendary Indian mathematician Srinivasa Ramanujan ji. His story is really a very remarkable. At very early age, at the age of 11 or 12, we have started showing his love towards mathematics, and he has solved many problems. Among the most famous work that he has done, Ramanujan number, I still remember, that is called magic number also. He has done, then Ramanujan square is also one of the another mathematical puzzle which enthralls all of us. He happened to be in UK, England for his research work, but because of ill health, he has to come back to India, and he was no more. At the age of 32, he passed away. He is still one of the Indian greatest mathematicians, and to honor his contribution, this day is celebrated as National Mathematics Day. The purpose is to install among students the love for the subject. The Department of Mathematics has successfully organized many workshops, seminars, and value-added courses. I congratulate the chairperson of the department, Dr. Neetu Gupta, along with her faculty members, for organizing this event. I am quite sure that the objective of the event will be achieved. With this word, thank you very much.
Thank you, sir, for sharing your words of wisdom and motivating our participants. Indeed, it is always a pleasure to have you with us. It gives me immense pleasure to welcome our today's expert, Professor H.C. Taneja. Professor H.C. Taneja is a professor in Department of Applied Mathematics, Delhi Technological University, Delhi. Sir has pursued PhD from Maharshi Dayanand University, Rohtak. Professor H.C. Taneja's research areas include information theory and its applications and stochastic processes. Sir has teaching experience and research experience of over 40 years. Sir has published more than 100 papers in various journals of international repute and conference proceeding. Sir has guided 13 PhD students and 7 MPhil students. Sir has delivered numerous invited lectures in various national and international conferences. Now, without any delay, I would like to invite Professor H.C. Taneja to deliver his lecture. Over to you, sir.
Thank you. Thank you, Dr. Manu. Professor, am I audible, please?
Yes, sir.
Yes.
Professor Sunil Garg, Professor Neetu Gupta, head of the department, and other faculty member, I congratulate you for organizing this event, and thank you for inviting me. So as far as my today's lecture is concerned, it's very quite general in nature. I'll be speaking on some application aspects of the mathematics. So I think I can start the lecture without any delay. So please let me share the screen. I think screen is visible, please. Yes. Dr. Manu, screen is visible?
Yes, sir.
Yes, sir, you are perfectly audible.
Okay, thank you. So I'll be speaking on the mathematics, some application aspects. There is a general saying, someone said that everybody is afraid of you. हर कोई तुम्हारे से डरता है. क्या तुम mathematics हो? That is a very general saying. Basically, the idea of mathematics just put some persons on the perplex some persons just with the idea of mathematics. They get fear about the subjects, and of course there is some problem is coming on the screen. It's not from my side.
Yes, sir. I'm trying, sir. Just give me a moment.
Please. I think some disturbance from your side, please. You have to make some person out from the meeting.
Sir, I'm trying, sir. Yes, please share your screen again, sir.
Is it okay?
Yes, sir. It's fine, sir.
Okay, please. Yes. Now, we constitute 1/6 of the world's population, and at least 2/3 of the global population today is going through the same crisis and turmoils. Basically, food, energy, water, healthcare, education, and employment are important requirements for people everywhere to live with prosperity. The world at large needs technological inputs in order to meet these needs, since the solution of these requirements can be found using science and technology. So these views had been expressed by our late Dr. APJ Abdul Kalam, former President of India, in his book, India 2020, A Vision for the New Millennium. We all know that he was a great believer that only the spread of education among the masses can solve these basic problems. And the use of achievement in the science and technology can lead to the economic growth of India and the world at large. Now, as far as science and technology is concerned, various disciplines constitute to the development of science and technology, basically by innovation, improving, and exploiting the ideas. And mathematics is one such collection of disciplines. Mathematics, when I say collection, it means statistics, it means computational techniques, the study of which inculcates the habits of rational thoughts. We say that it rationalizes your thoughts also. It put your thoughts systematically also and promote scientific temper in the young generation. That we try to view the things in a scientific manner when we have the knowledge of mathematics. Now, someone has said that in case you are good in analytics and have communication skill, you know some good analytical techniques, and you have good communication skill, you can achieve anything. आप कुछ भी कर सकते हैं. Okay, you should have power to analyze, you have the power of analytics, and you should have the power to express the things, then you can do wonder. So one thing is, sometimes we say that is mathematics a science? Someone say, no, mathematics is not a science. Physics, chemistry, bio, these are the science. But other may say that mathematics is not an arts. So what is mathematics? So mathematics is a science which stands apart from other sciences a bit. Yet it is a mathematical intervention that decisively confers the label science on any discipline. हम किसी भी सब्जेक्ट को साइंस तब कहते हैं जब उसमें एनालिटिक्स आ जाता है. Okay, you know that even these economics has completely become econometrics. Okay, so also the mathematics used in technology is reaching higher and higher level of sophistication. Basically, mathematics is a way of thinking in everyday life, and you cannot separate it. You can teach mathematics in the very early stage and are to the persons who are not familiar with the mathematics in a very practical way. For example, even you can explain the concept of fractions to heavy drunkard. Let us suppose you ask a drunkard, group of drunkard, which is larger, 2 by 3 or 3 by 5. They may not be able to answer. They may not have the analytical power, or they may not be in their complete senses to answer at that time. But if you simply ask them, which is better, 2 bottles of whiskey for 3 people or 3 bottles for 5 people, the answer will come immediate. And that will be, of course, 2 for 3. When you try to touch the mathematics from practical point of view, then you immediately get the answer. So basically, now if we say, when we start to learn mathematics, then I think it's a very beginning. Even a child of age 12 month knows that 1 is more than 2, because if you extend 2 toffees towards him, then he's definitely going to pick 2 instead of 1. So let us suppose that some hot arguments is going on between 2 young children when we were young, or we have seen the young one fighting in the street. Then a child says to the other that I will give you 1 slap. The other responds, I will give you 2 slaps. The previous child responds, I will give you 3 slaps. And sometimes this argument continues for some time. Then ultimately one child says that I will give you 1 more than you gave me, then you will give. It means that we know the concept that to every natural number, there exists a number n plus 1, which we formally study when we come to proper schooling at some level. Okay. Now, one thing, some concept of one-to-one correspondence. Can we recall when we studied the concept of one-to-one correspondence? Formerly, we studied when we were in the say middle or high school, and in a very informal way, we studied when we entered the 11th standard, one-to-one correspondence. Now, there were some tribes of Africa. They did not know any counting. उनको कुछ भी counting नहीं आती थी. Okay. And one surveyor analyzed that they take a group of cattle, herd of cattle for grazing, and they bring back the same numbers. Then how that was being done? Because they were not knowing any counting. वो कोई 40-50 कैटल्स मान लो लेकर जाते थे और सबको ही वापस ले आते थे. तो कैसे कर रहे थे वो? Actually, they were having the equal number of pegs. उनके पास उतनी खूटियां थी जितने कैटल थे. वो जब वापस लेकर उनको आते थे तो एक को एक से बांधा करते थे. अगर कम हो जाती, कैटल कम हो जाती, तो वापस जंगल में जाया करते थे कि some is a few cattle are less. और अगर हमारी अगर खूटियां कम हो जाती, तब उनको ये एनालाइज हो जाता है कि किसी और ग्रुप से हमारे पास कैटल आ चुकी है और हम उसको वापस. So that was the concept of one-to-one correspondence. Now we have seen the exponential number. There is a very, everybody exponential number. How you can just convince a small student that how this can be implemented in continuous accumulating of interest, or we can demonstrate the students how we can estimate the value of pi by just simulation methods. Okay. And there is some story of magic auditorium. You can just tell some small students. I will come to the main topic. Okay. For example, you have an auditorium which has 500 capacity. And let us suppose that the auditorium is full to the capacity. And let 10 VIP comes and they are to be placed. They are to be given the seat. Then situation becomes very awkward for the organizers, that where to adjust them, because seats are already full. Now, just try to imagine the beauty of the infinity number. Let us suppose you have an auditorium with the infinite capacity. I'm sorry, again, there is an issue. I hope that you're able to see it. Hello, Dr. Neetu.
Actually, I am trying, but I cannot identify the particular one and I am unable to.
I got it.
Yeah, this is happening for the first time. So just give me a minute.
No issue. I understand. Basically, should I share it again?
Yes, sir. Yes, sir.
Let
me see.
Okay, please. But again, the problem will come. Anyway, let us see. No, it has passed. No, we are not able to move the screen, please.
So there is an option from your side that you can you can take the permission from the candidates to write on your screen. This is option from your side who is sharing the screen.
From where?
On the top of a screen, there is an option more, and there is a disable attendee annotation.
Disable annotation for others.
Yes, sir.
I got it.
Yes, sir. Now no one can do that.
Yes, sir.
Thank you. It becomes something difficult, it's certain. There is only one way to identify, that they should have ID issued by your university only. Otherwise, it's very difficult to identify. I tell you. Please, anyway, no issue. It
Sorry,
happens.
sir.
Or nothing. It happens sometimes. We face problems. We also face problems. बहुत सारे कैरेक्टर हैं दुनिया में. एक्चुअली अब स्क्रीन मूव नहीं हो रहा, मुझे ये इशू आ रहा है थोड़ा सा. Let me join again then, please. Let me leave the meeting and join again, शायद. क्योंकि now I'm not able to move the screen even. Is it okay?
Yes, sir.
Yes, sir.
चलो,
Yes, sir.
दोबारा
सर जब आप स्क्रीन शेयर करेंगे तो आप वो ऑप्शन कर देना सर.
मैं वही कर रहा हूँ भाई, अब तो पहले
Yes,
कोई इश्यू नहीं है. ये screen is visible.
yes, sir.
Now go to more and this disable.
Yes, sir. It's fine.
Yes, it is done.
Yes, sir.
Okay. But this screen is not movable now. I don't know what has happened.
So you just have changed the screen now. First of all, it was showing some another.
नहीं नहीं.
Sir, some
हाँ,
choosing the
बोलिए.
मतलब PowerPoint presentation. If there is PDF, then it can be run.
I was running the PowerPoint presentation even. PowerPoint presentation ही मैं run कर रहा था.
Sir,
एक मिनट, please. Just. I don't know what happened.
Sir, is it possible that it can be converted into PDF? I think it will be movable. Ma'am, you are not audible.
सर ने मीटिंग लीव की है क्या तनेजा सर ने?
हाँ जी मैम, अभी ज्वाइन कर रहे हैं, उनका आ गया दोबारा।
अच्छा, आई थिंक सर पीपीटी पे अगर क्लिक करेंगे ना तब नेक्स्ट आ जाएगा, स्लाइड पे क्लिक करने से आ जाएगा। यस सर।
The field of mathematics has evolved tremendously since the great British mathematician G.H. Hardy. He proclaimed basically, he wrote his biography and a mathematician apology. He made a comment that that book was written in 1940 when his mathematical power was declining. And all of us, you know that he was the person who could identify the brilliance of Indian mathematician S. Ramanujan, whose birthday is being celebrated today. Now, he wrote that it was the very fact that pure mathematics had no practical application that made it beautiful and of permanent aesthetic value. He said that pure mathematics is quite beautiful because it is exact mathematics, but it does not has any practical application. That he wrote in 1940 when he wrote this book. Okay, and while applied mathematics, which is dull and trivial because we use a lot of approximation in applied mathematics, they have the application, but that mathematics is dull and trivial. That is not a beautiful mathematics. So basically, it is said that it is the reason that Alfred Nobel, you know, the Nobel Prize is given in 6 field, and mathematics is not included in that area, at that field. Okay. It was the same reason that mathematics did not enter Alfred Nobel's mind when he established the Nobel Prize, primarily to honor invention and discovery of great practical benefits to humanity. He considered that mathematics is not giving any practical benefit to humanities when he introduced the concept of Nobel Prize. Though if we Google about this, that why Nobel Prize is not given in mathematics, you can find some funny reason also that may or may not be correct. Okay, because of some personal reasons to the Alfred Nobels. Now, also we know that there are some very prestigious prizes in mathematics, Field Medal and Abel Prize, which are considered the Nobel Prize of mathematics. Now, Hardy, which made such a comment that pure mathematics has no use. He was expert in number theory. The number theory, Hardy's field of specialization, which he said was beautiful, but of little practical applications. Now, that is firmly rooted in public key encryption, which is widely used in data security. That number theory forms the basis as on today Now, you know that the public key encryption refer to the cryptographic system requiring two separate keys, one to lock or encrypt the system, and second to unlock or to decrypt the system, and neither key will do the both the function. For example, जैसे हम locker operate करते हैं, so the number theory forms the basis. That too much change came. Now, area of pure mathematics inspires problems in applied mathematics. It is this wonderful duality of mathematics, that the beauty of pure mathematics and its relevance in the real life problem, that we need to project among the students. You know that the Boolean algebra that was invented by George Boole in 1847, that was called at that time that it is all rubbish. कुछ भी नहीं है ये इसमें. It is of no value. And after 100 years, now this Boolean algebra forms the fundamental in the development of digital electronics. Your all digital electronics is based on the Boolean algebra. Okay, you know that Galois theories, that the theory of finite field. Galois was I think he was a French mathematician. His lifespan was from 1811 to 1832, just 21 to 22 years. He gave the theory of finite field. And that time, nobody took note of that it is just nothing. But today, it forms the basis of the coding theory. Coding theory is based on the theory of finite fields. So the use of mathematics is increasing in day-to-day life, and it has in fact taken a vital role in applied. The time has gone when we used to treat mathematics as an abstract and no application in the real world. You know the great equation in physics, energy equation, Planck's constant equations. So there is great relation between mathematics and physics. Now, basically the marriage between mathematics and physics, which was so enormously fruitful in past century, now that has more or less ended now. Because during the last 30 years, we have seen that mathematics is rushing ahead in golden age and a very luxuriant growth. Around this, mathematics has found another companion, another fiancé, and that is the engineering. Now, mathematics and engineering. And this marriage has resulted in a new dimension of application. You know, the development in the area of computer science. So mathematics, one of the area in which the mathematics has given wide application, that is the field of information theory and error correcting code. That is the field of the mathematical basis of the communication system. It is one of the area in which I personally work and have number of publications. The development, linear block code, cyclic code, BCH code, RS code. Now, all theoretical part is based on mathematics. If we study this linear block code, cyclic code, then we can find that how the maths is polynomial and how the binary system, how the octant system have helped in the development of this coding theory. So information theory basically is a theoretical concept of the information technology, because all theoretical base are from the information theory and designing base are the information technology. Now, Shannon in 1948 gave these two equations, that entropy of the system is equal to minus I from 1 to n pi log pi. This is the average amount of information in random message. And other as that C is equal to W log 1 plus S by N, where C is the capacity, W is the bandwidth, and S by N is the signal to noise ratio. Now, these two equations have led to far-reaching advancement in communication industry. though the digital communication industry developed in the time of the 70s, but their mathematical foundation came in the year 1948 when the Shannon derived these two equations theoretically. They form the basis of the communication. Now, this work of Shannon has led to far-reaching advancement in technology. Now, entire communication energy industry has gone through a revolution by using these two concepts. Now, the interaction of computing and mathematics is, of course, a very long-standing, and now the words are becoming synonymous. But you know that the mathematics naturally focus on the abstract concept and idea, while scientific field need and perform much computation. Now, with modern computer, modern and much faster computer, now many real-life problems which were not possible even before 1 or 2 decades, for example, in biology, in business, in banking, as well as other areas of life, can be solved efficiently. For example, in biology, the cell biology protein interaction need to be represented by precise mathematical models to explore the characteristics which are not obvious to the experimental. Now, computational modeling methods are used in e-business and strategic business management. The importance of mathematics has become so vital that even the areas like biology, sometime when we used to study, then perhaps we used to think that if you are taking biology, you may not need to take mathematics. For example, we were taking the medical combination, then physics, chemistry, biology was sufficient. Or non-medical, physics, chemistry, mathematics was sufficient. But now, even the biology has not been remain untouched from mathematics. The area of biotechnology, the area of bioinformatics, the area of nanotechnology, all their theoretical modeling is mathematics. You know that the bioinformatics is the application of computer science and information technology in the field of biology and medicine, specifically in the area of DNA computing. Now, you must have learned that before developing any vaccine for this corona epidemics, the DNA analysis was needed. Of course, their modeling is based on the fine mathematical and computing techniques. So this is now no area can be worked independently. Most of the area research in the area have become analytic. Now we study linear algebra. Maths is this linear equations. Now, we will not, it is not an exaggeration to say that linear algebra is a subject of central importance in both mathematics and a variety of other disciplines. Basically, it is used by mathematicians, statisticians, physicists, biologists, computer scientists, engineer, and social scientists, as far as linear algebra is concerned. Now, just as in the first semester, differential calculus gives us the basic knowledge about the function. Similarly, the process of linearization allows very difficult problems to be approximated by the quite easily manageable linear. Now, thanks to the very fast computing system, they can provide to give us better insight in the problem. Now, as the next speaker, you will be listening the linear programming, then all this is based on the linear. Yeah, okay. So another area which has been touched, the mathematical finance. This is one of the emerging area where where one should have a sound knowledge of mathematics and computing. Now, many insurance companies, banks, stock market have already starting hiring mathematicians to increase their customers and, of course, profits. Even a few of our publications, my publications, have been given the application of information theory to stock market and financial derivatives. And the papers have been very well accepted, and it's a very emerging area these days. Another is weather prediction model. The numerical weather prediction model, that is the NWP model, these are based on the real-time data, and it is based on the set of mathematical equation which governs the behavior of a system. And in this case, the system is your atmosphere. Applying the advanced computational technique, and now we are able to predict the model and predict the weather for the in a very exact way, say for the next 8 hours, next 12 hours, next 18 hours, and so on. Other important application of mathematics are in the aviation industry, GIS, and your GPS system, which you have in car. That is also the application of the mathematics. Of course, theoretical basis mathematics, and then you are modeling that. The mathematical theory of wavelet. I hope that you know that the wavelength, where both the concept of this frequency and time is considered. The development in theoretical computer science, financial mathematics, derivative pricing in your option pricing, call option and put option, that are based on the Black-Scholes models. I hope that a few of you must have learned that Black-Scholes model. Okay, so that is all the application of mathematics and statistics, basically. Okay. Now, computational geometric design has been widely used in industry, for example, car designing, etc. Another is your stochastic differential equations. Now, when you do modeling of a random system, for example, you are doing modeling for some stock price analysis, a physical system which is subject to some thermal fluctuations, then you come across the stochastic differential equation, that where the dependent variable is not deterministic in nature, it is the stochastic in nature. Stochastic in nature means it depends upon the probability. It depends upon the probability. So this is also an area is the mathematical application in the mathematical modeling of the epidemics theory. So stochastic models are there. So that is also based on the mathematical part. We need to train students in all the fundamental of mathematics and computer science with equal stress on common to both disciplines. We need to impart the training in such a way that the graduates are able to take up job in academia and industry or pursue higher study. Now, in our Delhi Technological University, we have, perhaps you may be knowing that we have a special BTech 4-year BTech program in mathematics and computing. And I think this was started in 2011. I was heading the department at that time, and first batch came in 2015. Many of the entrants were not very clear that will it turn to a BSc mathematics simply. But today you will be surprised to know that they are getting excellent job, sometime much better than the computer science. Because, of course, computer science is still the first choice, and mathematics computing, we are having students are opting at number 3 in our university. And sometimes they are able to get the better job because they know the computing technique and they know the mathematics also. So these students are fit for designing the software, and they are getting good admission for higher studies also. Okay, as far as career options are concerned, we know that number of career options are available in quantitative, computational, mathematical finance, that is investment bank, consulting firm, optimization and operation research, management consultancy, R&D, software development firms, scientific computing. As a data analysis, they are having a number of options. They are having a number of options in DRDO, ISRO, and computer-aided design industries. And of course, R&D, teaching and research career is always open for the mathematics. So we know that India was at the forefront of contributing to innovation in arithmetic, algebra, and geometry at a different period. The concept of zero originated from the India. No landmark contributions were made by early scholars such as Aryabhatta, Bhaskaracharyas, Brahmagupta, Madhva, and Leelavati. Then, after a somewhat dormant period, almost half a millennium, the revival of mathematical activities were triggered by the advent of S. Ramanujan. You know, we have Manu and Dr. Garg has already given some glimpse of his life, and Dr. Garg specifically mentioned that the magic number, and that magic number was the 1729. When he was in the hospital, and Hardy came to visit him in the hospital in UK, then he just asked that what was the car number. Then he told that his car number was 1729, that car number or taxi number. Then he immediately said that this is the number, smallest integer, which can be represented in two different ways, by the sum of two cubes. That 1729 is equal to 1 cube plus 12 cube, as well as it is equal to 9 cube plus 10 cube. Okay, so no number less than 1729 can be represented like this. So after independence S. Ramanujan, basically, there have been many other great mathematicians in India also in recent time, besides Ramanujan, most notably Harishchandra. You know that Harishchandra Institute of Mathematics. But there are not as many as there should be, given India's talent and legacy. We need to spot talent early and foster it. We need to teach our student about the great Indian mathematician like Panani, Pingala, Hemchandra, Aryabhatta, Leelavati, and Bhaskara. We will find that their work has been compiled in the form of excellent stories and sometimes poems. So their work will definitely inspire our young students. I hope that you must have heard the name of the Manjul Bhargava. Of course, he's an Indo-American, settled in USA. He's the winner of the field medal. Now, he mentioned that music, painting, and mathematics are very similar. And what is the similarity? Similarity is that all the three are creative. All the three are creative. Now, indeed, there are works of many contemporary mathematics of Indian origin, like perhaps you must have heard Karmarkar's algorithm, Viswanath constant, Rao-Blackwell theorems. Those who are familiar with the statistics. But unfortunately, their work is largely unknown outside the field of academia. जो लोग academia में हैं, उनको पता है शायद कुछ, बाहर नहीं है. उसके बाद, and they are seldom rich, और वो कोई बहुत rich या famous नहीं हुए. Now, in the USA, many Indian mathematicians are doing the good name, as I mentioned, Manjul Bhargava, Princeton, in the Princeton University, S. Vardhan in the New York University, Madhusudan of MIT, Ravikant in the Stanford University, and many more. So I hope that you must have read the news a few days back. Recently, Dr. Neena Gupta, mathematics professor at ISI Calcutta, has been declared the winner of the DST IMU Ramanujan Prize for the young mathematicians. She is the third woman and even the second Indian woman to receive this prize since its inception in 2005. Now, our government has tried to our government has given due importance of science as a vehicle for the progress and mathematics. Now, some notable work is also being done in some institutions. For example, Institution of Mathematical Sciences, Chennai, Indian Institute of Science, Bangalore, ISI, Calcutta, TIFR, Bombay, and some IITs and some other universities. Now, it is fair to say that India has indeed become a player of a reasonable standing in the international mathematical arena, but not a quite big. Very small country even are far ahead of us. For example, South Korea, Japan, and as far as big countries are concerned, they are far ahead of us. America, China, Russia, UK. So we are becoming a reasonable player in this aspect. There is a one saying from Professor Stephen A. Saxon that if we have evolved regional languages for the purpose of lying to one another, perhaps God has given us the universal language of music and mathematics so that we may address Him and each other in beauty and truth. He has specified that in different language we can lie with each other. हम एक दूसरे के साथ झूठ बोल सकते हैं, but music और mathematics दो ऐसी language है, we may address God in these language and each other in beauty and truth. So they are very beautiful and very truth means of communication. Now, I would like to end this just with one note. Now, important for our student and my other faculty member, the important aspect for us should not only be to become a knowledgeable person. A knowledgeable person is a good thing, but it should not be the only important aspect. Or a rich person or achieving some higher position. Basically, what we have, we should develop a very humble attitude of sharing and cooperation and working as a team. It is very important that we should work as a team. It is very important that we should try to share our resources and our knowledge. Now, we personally, we always remember such persons with great regards who sometimes extended such courtesies to us when we were in something in need. And always some person is always in a position to give and always in a position to need something. So those who have extended such courtesies to us, we always remember those persons with high regards. So last I will say with one couplet that वो शख्स जो तुमसे झुककर मिला होगा, वो शख्स जो तुमसे झुककर मिला होगा, निश्चय ही उसका कद तुमसे बड़ा होगा. So thank you very much. So adopt this attitude in your life and continue to do your work. Thanks for hearing me. Thank you.
Thank you, sir. Thank you so much for enriching us. Your experience and expertise of many years was pouring out of your words. We truly appreciate you that you always your time in gracing our various occasions. Thank you once again, sir. Sir, you have about so many applications. You have even touched every aspect of the science. You have talked about physics, even you have talked about the zero. You have proven the quote of Shakuntala Devi, without mathematics, there is nothing we can do. Everything around us is mathematics. Everything around us is numbers. You have proven it, sir. Thank you, sir. Thank you so much.
Thank you. Thank you.
Meenu ma'am.
Thank you so much, sir.
Yes, sir. Can we have a group photograph? So I request all of you to please turn on your cameras. It's done, ma'am.
Thank you. So, Dr. Neetu Gupta,
Yes, sir.
may I take leave of you?
Yes, sir. Thank you so much, sir.
I have some class also. So,
Okay,
thank
sir.
you. So see you
Yes.
sometime, please. Thanks for inviting me. Okay, bye. Take care. All the best.
Yes.
Okay, Dr. Garg. Thank you.
Thank you, sir.
Thank you.
Now, I invite another speaker, Professor Pankaj Gupta, sir. It's my pleasure to invite you, sir. Professor Pankaj Gupta, sir, is a professor in Department of Operational Research in University of Delhi. Sir is the head of the Department of Operational Research in University of Delhi. Sir has teaching and research experience of over 28 years. Sir has published more than 100 papers in various reputed journals. His research areas include optimization theory and application, fuzzy optimization, and portfolio optimization. Sir has guided 7 PhD students and 11 MPhil students. Sir is a member of Ramanujan Mathematical Society and Operational Research Society of India. Now I invite Professor Pankaj Gupta, sir, to deliver his lecture.
Yeah. Good morning to all of you. Thanks to Dr. Meenu Chawla for a nice introduction. And congratulations to Professor Neetu Gupta ji and her team to take initiative in organizing this event for the UG and PG students of your university. So it's my pleasure to be here for a talk. As advised by Professor Neetu Gupta ji, I have chosen the topic of my talk as linear programming problem and some related problems, or you can say applications of linear programming problem. So I will start with the contents of the talk. Let me just share the screen with you, and then I will deliver the contents. So the sharing option is here. Yeah. So yeah. So I hope that the screen is visible to all.
Yes, sir.
Yes, sir.
Okay.
So there is an option on your screen on the top right hand side on the top of your screen. There is an option that is saying more.
What is that option?
More, M-O-R-E.
M-O-R-E. Yeah.
Yeah. On the keep disable attendee annotation.
Let me just. Yeah. What?
Pankaj sir, there is an option in the, if you click on more, there is a drop down menu and you can click on disable attendee annotation.
Okay. Let me just see it. Let me screen share. I have already shared, and then on the more disable annotations for others. Yeah.
Yes.
Yes, sir. Yes, sir. Yes.
Okay, so there must be some, like some people who are trying to make some, like marks and all that. Okay,
Yes,
fine.
sir.
That's okay. So, yeah. So I hope that the screen is visible now.
Yes, sir.
Yes, sir.
Okay,
Perfectly.
and I've already disabled the annotation part as advised by the organizers. So the topic of the talk is linear programming problem. So Professor Taneja before me has mentioned about, many applications of mathematics, in different areas of applications. So one of the areas is like optimization and operations research. So that is basically not exactly, we don't put it in the applied mathematics category. It is altogether separate discipline, but it has a lot more to connect with the applied mathematics part. So here you have this linear programming problem, which is one of the most fundamental, decision making technique in operations research, and it is part of optimization. So it is an optimization problem, and optimization problem means there is something, which we have to optimize. And layman meaning of optimization is like in the sense of maximizing something or minimizing something. So here we have a decision making problem where, your goal is either to maximize the profit that you can achieve from the market, or the objective is to minimize the cost that is incurred on buying something from the market. So basically, either it is a maximization type problem or it is a minimization type problem. And as I said, this is one of the most fundamental problems. So it has been widely used in various areas of applications. But obviously, everything in this real world is cannot be expressed in terms of linear functions. So obviously, there is an extension to non-linear programming problem as well. But otherwise, linear programming problem has been extensively used in almost all kinds of application areas. Okay, so the most fundamental being the production planning problem, through which we can very easily explain the concept of linear programming problem to the students. So production planning problem can be any type of decision making problem, whether at a very small scale or maybe at a large scale. So we can understand uh, the logic behind, formulating a linear programming problem to a given decision making situation. So the most general problem of maximization and minimization we all study in mathematics, maybe at the 12th level or in the UG courses also, where we have seen like the calculus techniques can be applied to find out the maxima or minima of a given function. The function may be function of one variable or it may be a function of several variables, and the constraints imposed on those maximization or minimization are only the bounds on the decision variables. So we restrict the values of the decision variables in some interval. Okay, and then we find out the maxima or minima of the function. So that is the standard problem of optimization, and it is basically called as an unconstrained optimization problem, because the only constraints that we impose on the problem of maximizing or function or minimizing function are the bounds, on the decision variables. But when we come to the real world situations like linear programming problem, we also have to maximize or minimize a function. Since the name is linear programming, so the function is a linear function of the decision variables. There may be two variables, there may be three variables, there may be n number of variables, where n is very, very large from the real world applications point of view. So we have a linear function which is to be maximized or minimized. But here the difference is that we have some real world constraints which are also expressed as linear functions, or in the form of inequalities or equalities. So basically this type of problem falls in the category of constrained optimization problem. So we have two classes: unconstrained optimization problem and constrained optimization problem. So our focus here is on constrained optimization problem. So the fundamental problem being the linear programming problem. So let me just uh, go through some of the basics here. So I'm not going to teach here linear programming to the students, but I'm just going to show you the intuitive method. First of all, how to formulate a linear programming problem, how to solve it intuitively with the help of graphs. And of course, the graphs has limitation. So we move on to the standard method to solve linear programming problem, but not the mathematics of that method, just a idea how to progress with the iterations of the method called as a simplex method to solve the linear programming problem. And then I'll focus on two important applications of linear programming. One is in transportation problem and the other one is in assignment problem. Okay, so this linear programming problem basically, as I said before, it uses a mathematical model to describe the problem of concern. And the adjective used here is linear, which means that all the mathematical functions in the model are required to be linear functions. Whether you formulate an objective function or you formulate the constraints, they are all linear functions of the decision variables. And the programming word here does not mean actually a computer programming. It is simply a synonym for planning. And then this linear programming problem involves basically the planning of the activities to obtain an optimal result. That is a result uh, which basically satisfies your goals in the best possible manner. Okay, and this optimal result is obtained from uh, there are lots of solutions available, and then we have to choose the solution which is the optimal solution in the sense of giving the best possible value of your goal, if it is a maximization of profit or whether it is a minimization of cost. So I take the example of a very again some the scratches are coming, so मैंने तो इसको डिसेबल कर दिया है. नीतू जी, Professor Neetu ji, can you hear me?
Yes, sir. Yes, sir.
Yeah, but there are few, like scratches coming on the screen.
Sir, sir, only one scratch is there. That is M.
Yeah.
Sir,
Yeah.
please rub it. Yes, sir.
Or sir, you can simply re-share your screen and then you can directly choose the option in the more.
Okay, I'll do that. So I stop the sharing.
Yes, sir.
Okay, fine. I'll do that. Give me a second, okay? Is that okay?
In the more option, you can select the same features.
Yeah, but I have already disabled it. So
Okay, sir.
now,
Yes.
yeah, it says now enable. So obviously the
Yes, sir. Yes.
okay.
Okay. Fine.
So this is one of the examples of understanding a problem and then how to formulate a linear programming problem for the given situation. So this is basically related to a production planning problem. We are basically, two types of products are manufactured, and these products are labeled as high quality tables and high quality chairs. Obviously, when you make some products, you sell them in the market and then you can generate some profit from them. So the profit contributions are given here. So if you sell one chair in the market, then you earn a profit of $15 or 15 rupees, whatever you can call it. And if you sell one table in the market, then the profit is 21. Okay. Then the plan is for a weekly production. So basically, to make the two products, you need some resources also. And one of the critical resources to use here is labor. Uh, uh, in fact, two resources are here. So one of the critical resources is the labor, and the other one is the wood. And both these resources, the labor hours and the wood, they are not available in unlimited supply. So there is a restriction on the availability of these two resources to carry on with your weekly production. So the requirements of these resources in making these two products are given here. Each chair requires 4 labor hours and 8 board feet of wood. So this is the requirement for each chair. Similarly, for each table, it is given that uh, we need 3 labor hours and 12 board feet of wood. So these are the requirements of the two resources in making these two high quality products, the tables and the chairs. And as I said before, the availability of the resources is limited. That is why sometimes we also call this as a linear programming problem to arrive at the best possible decision considering the scarce availability of the resources. That means the resources are available in limited supply, not unlimited supply is there. Okay. So the availability of labor hours, so you have about 920 hours of labor available for weekly production. And also the wood availability is 2400 board feet of wood that is given to you for a weekly production. Now, besides the requirement of the resources, there are some other restrictions which are basically to satisfy the market conditions. So the market conditions are put here in this particular sentence. The management requires that at least 40 tables and at least 4 chairs to be produced for every table produced. These are the conditions which are being imposed here as per the market requirements on the demand of the products according to the demand of the products in the market. Then obviously this is a production planning problem. So the objective here is to maximize the profits, and the profit can be maximized only by making the products and selling them in the market. So how to decide on the level of the two activities? That means the two activities to be carried out here is production of tables and chairs. So how much should be the level of each activity? That means how many units of tables and how many units of chairs you should produce in order to maximize the profit from the market. That is the problem. So, but the objective to maximize the profit is constrained by the availability of resources, and also there are market requirements in terms of the demand of the products in the market. So let us see how do we solve such kind of a problem, decision making problem with the help of linear programming problem. So what we do is that we first of all formulate a linear programming model for this given situation, and then we try to solve it and find out the solution which is called as an optimal solution that gives you the maximum profit in this particular case. So if we look at this thing, so now you can see that so this is the problem. So the two products here are basically the chair and the tables. So you can visualize them here. So then the next thing is that we are given the profit per unit chair and per unit table. So I've already described for you. This is $15 for each chair and $21 for each table. Then also we have the requirements of the resources. So we need 4 labor hours for each chair and 3 labor hours for each table. Then we also have the requirement of wood. So we have basically 8 board feet of wood required for each chair and 12 board feet of wood required for each table. And then we have also the availability of the resources given over here. So availability here is 2400 board feet of wood available. And also we have the labor hour. So this labor hour is, as I said before, we have 920 hours of labor available for weekly production. Okay. And the market requirements, as far as the demand of the products is considered, so we have the requirement of at least 40 tables, and also we have so we need to have at least 40 tables, and then also we have at least 4 chairs should be produced for every table produced. So that means if you have a table here, then for each table you should have at least 4 chairs. Okay, so this is like the visualization of the problem. So we have this is your chair, and this is your table. So these are the requirements, and the complete data that we have to formulate the linear programming model for this particular decision making situation. So the decision is, of course, how many chairs and tables to be produced in order to maximize your profit. Okay, so now let us look at the formulation of this problem. So basically, when we have understood the problem, so we know that the decision is regarding like how many chairs and how many tables to be produced to maximize your profits. Okay, so we know that we have to take two decisions regarding the number of chairs and the number of tables to be produced, okay, using the available resources and satisfying the market requirements in terms of demands of the two products. So first thing is that for any given situation like this, we have to understand the objective of our problem. So here the objective of the problem is very clear. It is to maximize the profits. Okay, but how to achieve this objective? That is by making choice of your decision variables, and then for using those decision variables, we give the mathematical formulation to the objective function and also the constraints of the problem. So here you can see that there are only two products involved, chairs and tables. So we have to take the decision regarding the production of chairs and tables. So basically we choose two decision variables here. One is labeled as x1, which represents the number of chairs produced in a week, and the second variable is x2, which represents the number of tables produced in a week. Okay, and then using these two decision variables, we write the mathematical function to represent our objective function and to represent our constraints. So there are many important properties of linear programming problem. One of the important properties is the additivity property. So basically what you can do is that you can add the individual profits to come up with a composite term that represents your total profit. So here the individual profits can be obtained from the chairs and tables. And another important property is the proportionality property. So as you can see that every chair fetch you a profit of $15. So if you make one chair, or you make 10 chairs, or you make 1,000 chairs, the profit will not change. So it will remain same. So we can simply multiply 15 by x1, the number of chairs, to get the profit from the total number of chairs that we are making, that is x1. So the individual profit from chairs comes out to be 15x1. Similarly, from every table you get $21 as the profit. So if you make x2 number of tables, then the profit that you can generate from the tables individually is 21 multiplied by x2, and then you can add on your individual profits to get a composite profit, that is the total profit from both the products. So that is represented here as this function 15x1 plus 21x2. And since the objective is to maximize this function, so we have this maximization term on the left hand side, and this z represents the value of the total profit which you are going to get. Okay, so this value we have to maximize, but this maximization is subject to certain constraints. So we look at those constraints one by one. So as you can see that so we have basically now to formulate the constraints here. So the constraints can be formulated in this manner. So basically there are first of all requirement of the resources, and the two resources are the labor hours and the requirement of wood. So you can see that the consumption, first of all, the availability of the wood is given to us, that is 2,400 board feet. So this is the maximum wood is available. Okay, but the requirement for these two products are given here. 8 board feet of wood for each chair. And since we are deciding on to make x1 number of chairs, so the requirement of wood would be 8 multiplied by x1. And similarly, each table requires 12 board feet of wood. So if we are deciding to make x2 number of chairs, then the total requirement of wood for chairs would be 12 multiplied by x2. And when we add these two individual requirements, we get the composite requirement, that is 8x1 plus 12x2. This is the total requirement of wood to make x1 number of units, x1 chairs and x2 tables. But the total consumption or requirement of wood cannot be more than the availability. So availability is 2400. So we have this first constraint the second constraint 8x1 plus 12x2, and this has to be less than or equals to 2400. That is the maximum amount of wood available to you for production. Then the second constraint is related to the availability of labor hours. So you can see that each chair requires 4 labor hours. So x1 chairs will require 4x1, and each table requires 3 labor hours. So all the tables together will require 3x2 labor hours. So when we add these two, the total requirement labor hours becomes 4x1 plus 3x2. And the availability of labor hours is given to you is 920 hours. So total requirement cannot be more than the availability. So we have second constraint here, that is 4x1 plus 3x2, and that is less than equals to 920. So you can see that and of course there are two more constraints here, and that these constraints are that you also need to have at least 40 tables. So there is a lower bound on the production of tables, and since the production of tables is denoted by x2, so there is a lower bound on x2. X2 has to be greater than or equals to 40. So at least 40 tables must be produced. And the second requirement is that for every table produced, there must be at least 4 chairs. So we have x1 is the number of chairs. Okay, and if you have x2 is equals to 1, so that means one table is produced, so x1 must be greater than equals to 4. At least 4 chairs should be there. If x2 is 2, there must be at least 8 chairs, and so on. So you have the condition x1 is greater than equals to 4x2. So these are the constraints of the problems, which are also formulated as mathematical functions using the decision variables, linear functions using the decision variables. And the constraints here are expressed as inequalities. You can see that the inequalities are less than equals to type. Inequalities are also greater than equals to type. And sometimes you are also given the equations. So basically the system that we write down here as the constraints part. So the functions can be represented by the inequalities and can also be represented by equalities. So when we look at the complete problem, now this is a complete mathematical programming for a mathematical model of this particular problem, linear programming model. So we have to maximize z, which is 15x1 plus 21x2, subject to these constraints, which I've already explained. Okay, so we have the first constraint related to labor availability. The second one is related to the wood availability. The third one is basically regarding the minimum requirement of tables in the market. And the fourth one is related to the production relationship between the chairs and the tables. And then finally, we have this non-negativity restriction. Both the decision variables are restricted to be non-negative in sign. This is precisely because whenever we have to take the decisions in the real world situations, the negative values do not make any sense here. So then there is a trivial constraint here called as a non-negativity constraint, which is imposed on all the decision variables of the problem. But it is not that in all linear programming problems the variables can only be 0 or positive. There are some situations where the variables can take the negative values also, and in such cases we call the decision variables to be unrestricted in sign. Okay, so this is the complete mathematical formulation of this linear programming model for this particular given situation. Okay, so now once we have formulated the model, so basically what does this model says? You basically find out, first of all, because it is a constraint optimization problem, so this maximization of the objective is subject to satisfaction of these constraints. And satisfaction of these constraints is that you have to find out those pairs x1 comma x2 which can satisfy all the constraints of the problem simultaneously. So it is not that some constraints are satisfied and some are not. You have to find out only those solutions x1 comma x2 which satisfies all the constraints of the problem simultaneously. So basically we have to, when we look at it graphically, so we will see that we'll come out with the intersection of these constraints. So we come up with a space which is called as a feasible space or the feasible region. And basically from that region, if you pick up any value of x1 and x2, that will satisfy all the constraints of your problem. And it is called as a feasible solution. And then from so many choices of feasible solutions, we have to select the one which is an optimal solution. Optimal solution here in the sense, it gives you the maximum value of Z, that is the profit given as 15x1 plus 21x2. So let us now move on further, with the intuitive method, that is to how to solve the linear programming problem graphically. We are like taking up a different problem here for the solution purpose. So now before coming to this, let me also give you an example of a minimization type of linear programming problem. So like this is production planning. So in production planning, the profit is mostly the maximization of profit, but in real world situation, there are mathematical models where you can consider simultaneously more than one objective or goal. Like here, the only objective or goal is to maximize the profit, but sometimes in the real, or not sometimes, in most of the times, the real world situation requires the achieving multiple goals or multiple objectives simultaneously. Like in a production planning problem, you can have a profit maximization. You can also have a capital minimization. You can have other constraints also, like the employees working with you, they must have the highest possible satisfaction. Okay, so there are various type of goals or objectives that you can associate with in real world situation problems. So here the linear programming means only one objective is to be considered at a time, whether it is maximization or it is minimization. So when we look at the minimization case, so one of the most common problem to explain the minimization type linear programming problem is diet problem. So basically it is like it goes like you have been advised by your dietitian to take certain nutritional elements in your daily diet. Okay, and the minimum quantity of the nutritional elements has been specified, which should be your daily intake. Okay, and you can satisfy the requirement of nutritional elements from the food that is available in the market. So there are different types of foods available, and each food has different mix of nutritional elements. Okay, so your objective is to satisfy your minimum daily requirements of nutritional elements, subject to minimization of cost of purchasing. So we can we can look at this problem in a different way. So if I consider it as that x1 and x2 basically relates to the two types of foods that are available in the market, which you can purchase, and they both contains the different proportions of the nutritional elements which have been advised to you in your daily diet. And the cost of purchasing per packet of food one is $15, and the cost of purchasing of per packet of food two is $21. Then the individual cost of purchasing of the first food type would be 15x1, and the other one would be 21x2. And when we add these together, this is the total cost of purchasing of two food types from the market in order to satisfy your daily requirements of the nutritional elements. So in that case, this objective function would not be maximization type, it would be a minimization type objective function. So we can say that we have a function minimize z is equals to 15x1 plus 21x2. Okay, then let us say that the two nutritional elements, so here we have two resource constraints. So we can call them as the two constraints related to the requirement of nutritional elements. So let us say that the two nutritional elements required in your daily diet are A and B. And let us say the minimum quantity that is required in your daily diet is 920 units of the first type of nutritional element, and 2400 units of the second type of nutritional element. And both the food packets, they contain both types of nutritional elements but in different proportions. So let us say that 1 unit of the first type of food packet that contains 4 units of the first type of nutritional element, and the second food type contains 3 units of the first type of nutritional element. So the total intake would be 4x1 plus 3x2. But in this case, because the minimum requirements are satisfied, so the inequality would be of different type. It would be a greater than equals to type inequality, and greater than equals to 920, because the minimum requirements have been specified. Similarly, in the for the second type of nutritional element, the availabilities are, let us say, 8 units in each packet of x1, that is the first food type, and 12 units in each packet of the second type. So the total intake would be 8x1 plus 12x2, but again the minimum requirement is satisfied, so that will be greater than or equals to 2400. These constraints can be ignored because these are as per the market requirements. There could be some other requirements in the diet problem, and then if we leave out these two constraints, then the non-negativity constraint will be there, that is x1 and x2 both are greater than equals to 0. So this way we can come up with a minimization type objective function, mostly related to the cost minimization, that is the cost incurred on making some purchases from the market. So we have two extreme type of problems: the profit maximization problem and cost minimization problem. So now I go on to show you intuitively how this problem can be solved graphically, but graph has limitation because we can visualize it in two-dimensional plane, and it's difficult to go beyond two-dimensional plane to have a clear-cut visualization of the problem. So whenever we have a problem having more than two variables, okay, and of course the graph is suitable when we don't have too many constraints also, because ultimately you will see that the feasible region is detected, or the feasible space is detected by taking the intersection of the individual regions. And these individual regions are the regions which are satisfied by these constraints individually. So when you have large number of constraints, it's quite difficult to find out the intersection of the all the constraints. So graph is suitable. It is basically intuitive method only to explain you how actually the algebraic method solves the linear programming problem in an iterative manner. So let us go to the problem. So this is the problem that I'm considering for the solution purpose. So this is maximization Z, which is equals to 3x1 plus 5x2. And it is subject to these three constraints. And then the fourth one is, of course, the non-negativity restriction. So we have x1 less than equals to 4, 2x2 less than equals to 12, 3x1 plus 2x2 less than equals to 18, and x1, x2 are greater than equals to 0. So as you can see that there are two variables, so we can choose two axes in the graph. One axis corresponds, the horizontal one corresponds to the variable x1, and the vertical one corresponds to the variable x2. So as you can see, if there are three variables, then obviously the choice of third axis will give more and more complexity to the graphical method. So it is not advisable. So basically, as I said before, the solution of the linear programming problem is defined in two categories. One is the feasible solution. So feasible solution is basically the one which satisfies all the constraints of your problem. And when I say all the constraint, it includes the non-negativity restriction as well. And then from the set of feasible solutions, we have to find out the one which gives you the maximum value of the objective function, which is represented here by Z. And that solution will be called as an optimal solution. So what we do is that because the inequalities cannot be plotted directly on the graph, so we first of all consider the boundaries, and boundaries are basically the equations that we can consider from these inequalities. And once we plot the boundaries, then any line that is plotted on the space the graph, that is going to divide it in two half spaces. So we have to choose the half space according to the requirement. And once that is done for one of the constraints, then we do it similarly for all the constraints. And then we look at the intersection of these, the area. And if there is a common area that is being satisfied by all the constraints, we call it as a feasible region or the feasible space of the problem. So let us now look at it. So we have, you can see I take the constraints one by one. As I said before, we have to draw the boundaries first, and these boundaries are basically represented by the equations obtained from these inequalities. So if we consider the first constraint, x1 is less than equals to 4, then the boundary corresponding to this constraint is x1 is equals to 4, and x1 is equals to 4 is very easy to draw on the graph. So you can see that this is the vertical line. So it is going to bound the restriction, bound the values of the variable x1. So that means x1 cannot be more than 4. So anything that is here. Now, first of all, you see that these are x's, and since x1 and x2 are greater than equals to 0, so basically we are using the first quadrant only, because the decision variables are non-negative in nature. So basically we are restricting ourselves only to the first quadrant. Okay, now in this first quadrant we have to then take the other constraints one by one. So one of the constraints we have taken here is x1 is equals to 4. So x1 is greater than equals to 0, but it cannot be more than 4 because of this restriction. And now this is the line that we have drawn here. X1 is equals to 4, the boundary. And you can see that when we draw this line on the plane, it divides it into half spaces. So we have to look at the half space that we have to consider, that is below this line or above this line. So that can be easily detected by looking at this point 0. This is 0, 0, both x1 and x2 are 0. So if this point is included in your feasible region for this particular constraint, the half space chosen would be this one. Otherwise, the half space chosen would be this one. So as you can see here, this 0, 0 is part of the feasible region for this individual constraint. So we have considered the half space on this side of the line. So you can see that this shaded portion, this is the area from where you can pick up the values of x1 and x2, because this constraint does not have any involvement of x2. So x2 can be anything here, satisfying 0 or more than 0, any positive value. And but x1 has to be in this area, that is less than 4 or at most equals to 4. So this is the first constraint that we have drawn on the graph, and we can see the feasible region of this constraint according to the specified inequality. And this thing we are going to do for all the other two, for the rest of the two constraints. And then we choose a common area, common feasible area. So that is the feasible space of the problem. So let us look at the second constraint. So as you can see that now the second constraint is 2x2 is less than equals to 12. So if we look at the boundary here, so we get x2 is equals to 6. So x2 is equals to 6 is this vertical horizontal line that is being drawn here. Now you can see that both the values of x1 and x2 are restricted. So x2 is restricted up to this line. It can have any value here, and then but since x1 is also restricted, so if we look at the common intersection of these two constraints, then the only area that is feasible is marked by this number 2, because in this area you have x1 is less than equals to 4, and also x2 is less than equals to 6. But otherwise, if you go to area number 1, then you can see that the second constraint is violated, because here you have x2 more than 6. And if you go to the area number 3, then you can see that here the first constraint is violated because x1 is more than 4. And if you look at this empty space here, then obviously both the constraints are violated. That means first is not satisfied, second is not satisfied. So from these three areas, we can choose only the area number 2, because that is the only area where both the constraints are satisfied. So with these two constraints and together with the non-negativity restriction, the feasible region is obtained as the area number 2, but still we have one more constraint to plot. So let us see the third constraint. So now you can see that this particular constraint is a line. So 3x1 plus 2x2 is less than equals to 18. So we can consider a boundary. 3x1 plus 2x2 is equals to 18. And then by giving getting two trivial points of this line, by putting x1 is equals to 0, we can get x2 is equals to 9. So this is the point 0, 9. And by putting x2 is equals to 0, we can get x1 is equals to 6. So this is the point 6, comma 0, and we can join these 2 points to draw this line which represents your boundary of this constraint. And once again, to see that which half space we have to choose, the above it or below it, we can substitute x1 and x2 both equals to 0, and you can see that 0 is less than equals to 18. So this point is part of the feasible region of this constraint. So we choose the half space which is below it. So now you can see that from the previous case, this was the feasible region. And now when we have drawn an extra constraint, some more portion has been removed, because that is the portion which is not satisfied by this constraint, because this constraint means less than equals to 18. So any part which is here, that is going to violate this constraint. So basically, when we look at the common area, so the common area comes out to be this shaded area. And this shaded area means any point here in this region giving you values of x1 and x2 will satisfy all the constraints of your problem, including the non-negativity restriction. And one of the important thing about the linear programming problem is that the feasible region is a very special type of region. It is closed and bounded region, and also it is a convex set. I don't know how many of you know the concept of convex sets, but intuitively, convex set is a set, where if you take any two elements of the set, the line segment joining that would completely lie in that particular set. So all the solid figures like this, they are convex sets, and you can see that it is in the shape of a polygon, and it has certain corner points. So when we solve the linear programming problem graphically, of course, there is a lot of mathematics behind it. So that is outside the scope of this lecture. So intuitively, we can concentrate only on these special points, which are the corner points or the vertices of this feasible region, which is in the shape of a polygon. So you can see that the corner points here are this corner point, second corner point, third corner point, fourth corner point, and the fifth corner point. So there are 5 corner points, but theoretically, if you look at the feasible space, there are infinite number of solutions, feasible solutions here. And obviously, it is not possible to enumerate each of these solutions and then evaluate the objective function value at the solutions, feasible solutions, and get the maximum or the minimum of the objective function. So basically, we do it with minimum efforts, and the minimum efforts boils down to the choice of corner points here. There is a reason behind that. So we have the linear programming because these corner points are basically related, are mapped to the basic feasible solutions algebraically. And we have a fundamental theorem of linear programming that if an optimal solution exists, then at least one of the basic feasible solutions has to be optimal. So since these corner points are mapped to basic feasible solutions algebraically, so these are the only points of concern to us. The linear programming problem, if it has an optimal solution, the solution can never be inside the feasible region. It cannot be on the boundary points also. Of course, the corner points are the boundary points, but they are special type of boundary points. So basically, the only point of concern for us are corner points, which are always limited in number. In very, very rare cases where you have a very large scale linear programming problems, there you have difficulty in getting a solution of the linear programming problem in a reasonable number of in a reasonable time. Otherwise, the corner points for most of the problem are finite in number, and you can always get the solution of the linear programming problem in finite number of iterations, except few situations which are like very rare situations. Okay, so now once this feasible region is drawn, so we can remove the other points from here, and we can concentrate only on this region, which is called as a feasible region. And now you can see that the corner points which are of interest to us are A, B, C, D, and this point O, which is the origin. Okay, and this origin is known to us very clearly. Okay, this point D is also known to us. This point A is also known to us. Only thing is that the point B is to be obtained and the point C is to be obtained. So B is the point of intersection of the third constraint with the second constraint. That is the boundary corresponding to third constraint and the boundary corresponding to the second constraint. Similarly, this point C, it lies on the boundary corresponding to the first constraint and the boundary corresponding to the third constraint. So you can easily find out these coordinates. So the coordinates of A are clear to you, 0, 6, and the coordinates of D are clear to you, that is 4, 0, and the coordinates of O are clear to us, that is 0, 0. So we can find out B and C in the way I have told you just now. So when we evaluate the other two, so basically the point B comes out to be 2, 6 because it lies on the boundary given by the second constraint and the third constraint. Similarly, we have the point C, which is obtained as 4, 3. It lies on the boundary created by the first constraint and the third constraint. So this way, all the points have been enumerated, the corner points, and now the job is very simple. You can evaluate the objective function value, that is Z, given as 3x1 plus 5x2 corresponding to all these points. And then from these points, you can pick up the optimal value in the sense of maximum value of Z. And you can see that the maximum value of Z is 36, which is attained at the point B. And the point B is 2, 6. So x1 is equals to 2 and x2 is equals to 6. So this is what we have the solution to this problem. X1 is equals to 2 and x2 is equals to 6 with the corresponding value of Z is 36. So this way, the maximum value we can find out, which is achieved at the point B, because the work here is only restricted to evaluating Z at the identified corner points of the feasible region. So, and then there is another way also of identifying the optimal solution of your linear programming problem. And that is basically called as the ISO profit line. Okay, so the maximization problem is this problem. And you can see that 3x1 plus 5x2 is equal to Z also represents a line. So what we do is that we give some initial value to Z. Let us say this is the initial line that we draw from the objective function corresponding to a given value of Z. And then we see that how it can be improved. So we have to identify the direction of improvement in which, we can keep this line moving parallel to itself. Okay, so once the direction of improvement is identified, clearly the direction of improvement here is the upside direction, because when you increase the value of Z, this line will also shift. So this line will move parallel to itself. Okay, and then what happens when we draw it like this? So you can see this was the initial line. You increase the profit further, it goes to here, then it goes to some more lines are drawn here, and then finally you get this line, which leaves the feasible region, but before that it crosses the feasible region exactly at one corner point, and that is the optimal point. So this approach is called as the ISO profit approach, where you can identify the maximum profit or the optimal profit by drawing these objective function lines corresponding to arbitrary values of Z, and then identifying the direction of improvement. So you have to shift the line parallel to itself, but in the direction of improvement. And a stage will come when the objective function line crosses the feasible region and at exactly one point, which is identified as an optimal solution. And if you move it any further, then you can see that it leaves the feasible region. So the profit that is achievable corresponding to those values of Z, they are not from the feasible region, they are outside the feasible region. So this is also called as ISO profit line approach to identify the optimal solution of your linear programming problem. So whether you evaluate the corner points, so basically the simplex method, the algebraic method, works on the first principle, that is it identifies the corner points, and then of course it chooses a path along which it moves along the edges here to move from one corner point to another point in the search of an optimal solution. So this is like these. Then there are other the few terminologies regarding the solution of the linear programming problem. So in general, this is the form of the linear programming problem. You can see that this problem is either maximization type or minimization type. It involves n variables. The variables are labeled as x1, x2 up to xn, and these are the cost coefficients. So like you have seen the objective function here, Z is equals to 3x1 plus 5x2. So 3 and 5 are the cost coefficients. Here you can call them as the profit contributions. So we have these are the cost coefficients, that is the coefficients of the variables in the objective function. Then usually it is considered as a set of m constraints and n variables. So you can see that there are inequalities which can be of less than equals to type, greater than equals to type, or it can be an equation. These are the right hand side values, which are basically the availability of the resources, and these left hand side basically the values, the consumption rate of the resources for each product. So you have n products to be considered. These are the consumption rates. So the left hand side represents the total consumption of the resource, first resource in making of n products, and the availability of the resources is b1. So if it is availability, it will be less than equals to type. If it is some kind of requirement, minimum requirement, it will be greater than equals to type. And if it is exactly satisfied by value, it will be an equation. So this way we can have the set of m inequalities okay, in n decision variables. So this is the general form of the linear programming problem. So when we call it as a solution, feasible solution means any solution, this is a n tuple having components x1, x2, x3 up to xn. So any n tuple that satisfies all these constraints including non-negativity, we call it as a feasible solution. And if the solution violates at least one of the constraints here, that solution will not be called as feasible, that will be called as infeasible solution. And then, as I said before, from the feasible solutions, the one that gives you the maximum z or the minimum z is called as an optimal solutions. Okay, so there are special cases of linear programming as well. Like not every linear programming problem has an optimal solution. So there can be a case of no optimal solution to a linear programming problem, which basically corresponds to two subcategories: no feasible solution, or there is a case of unbounded solution. And then there could be multiple optimal solutions also to a linear programming problem. So in the next slide, I will show you. This is the multiple optimal solution case. So you can see that the feasible region is the shaded region. And now this red segment, which is the boundary segment as part of the feasible region, basically when you draw the this line, as I said before, this line, so here it crosses the feasible region exactly at one point, and then it leaves the feasible region. In some cases, when you draw the objective function line, it will coincide with one of the boundaries of the feasible region before leaving it, and that is the case of multiple optimal solutions. And if you enumerate the corner points, you will see that the corner point here and the corner point here both gives you the same value of the objective function, that is the maximum or the minimum value. So this line segment is identified as the one that gives you multiple optimal solutions to the linear programming problem. Each solution will give you the same objective value, maximum or minimum value, but you have different combinations of production plans or the activities. So we have the one point here and 1 point here, and then we take the convex combination of these 2 points to generate many optimal solutions. So one of the features here is that you have these 2 points. So these 2 points are adjacent corner points. So adjacent corner points are those points basically which are directly joined by an edge of the or the boundary of the feasible region. So if you look at this point and this point, they are not corner points, adjacent corner points, because they are not directly joined by a boundary or the edge of the feasible region. While this point and this point are adjacent, this point and this point are adjacent, these two are adjacent, these two are adjacent, these two are adjacent, these two are adjacent. But if I take this point to this point, it is not adjacent because they are not directly joined by an edge or the boundary of the feasible region. So this is the case of multiple optimal solutions. Then we have no feasible solution case also. Let us look at this problem. When we draw the feasible region, then we find there is no common area that is satisfied by all the constraints of the problem, including the non-negativity restriction. So the feasible space of the problem is an empty set, and hence we call it as a no feasible solution case. The problem does not have any feasible solution. And then we have the case of no optimal solution. So no optimal solution can be in case of the problem is not feasible, and no optimal solution can also be in the case when the problem is feasible, but there is no finite bound on the objective value. That means there is no finite upper bound in case of maximization, and there is no finite lower bound in case of a minimization. So as you can see here, the constraints are plotted on the graph, and the feasible region is identified to be this region, and this region is very different from the region that we have considered before. Like this region, this is closed and bounded region, but here you can see that this region is closed because the boundaries are included, but at least one of the boundaries is left open, so this region is not bounded. So that means you can go to any extent in this direction to increase x1 without violating any constraints, or you can go to this direction any extent by increasing x2 without violating any of the constraints. So the region is unbounded. Okay, and if you, since you can increase x1 and x2 arbitrarily large, so obviously z will also be increased to arbitrarily large when you increase x1 and x2. So there is no finite upper bound on z, and hence we call this problem having an unbounded solution, because the bound objective function value is not bounded. So no optimal solution case can occur in two different situations: when the problem has no feasible solution, and when the problem has feasible solutions, many feasible solutions, but the finite bound cannot be obtained for the objective function. Okay, so Neetuji, how much more time I have with me?
Sir, actually you started at near about 11:15, so it's almost over, sir.
It's almost over. Okay, then I'll not go into the transportation and assignment problem part. I just complete this linear programming part only. So there is a I mean, like, it's not possible to explain simplex method here in this lecture, so I just show you how does it work. It is an iterative method. Okay, so
Okay,
basically,
sir.
yeah, as you see that we have the limitations in as far as graphical method is concerned. So you cannot have more than two variables, and of course the number of constraints should also not be large. So we have no dependency on the graphical method to solve linear programming problems. So it was taken up only to give you an idea that how the linear programming problem is solved by looking at some particular points of concern in from the feasible space or the feasible region of the problem. So this simplex method is an algebraic method which can solve the linear programming problem, any given linear programming problem, in a reasonable time, irrespective of the number of variables and the number of constraints of the problem. Although there have been developments regarding the interior point algorithms for linear programming problem, but still date, this simplex method, which was developed by George B. Danzig in 1947, this is still date is considered as one of the best methods to solve the linear programming problems, because despite besides the solution, it gives you so much other information, that is used in many other important aspects of linear programming problems. So despite it's not very fast algorithm as compared to interior point algorithms, but this still is considered as one of the most standard best widely used method, and also the standard method to solve linear programming problems. So this is a general procedure, does not depend on the number of variables and the constraints. And with the help of the advancement in computers, the method can always be executed on computer, and you can, and the software packages are also available to solve linear programming problems arising in real world situations, which are large scale problems in terms of variables and constraints. Okay, and these packages can make use of simplex method to give you the solution very quickly, depending on the speed of the computer and the memory allocations and all that. So we have it is an algebraic procedure. Okay, but the underlying concepts used in the simplex method are related to geometry that we have seen just now. Okay, so basically we look at this problem again. Okay, so the corner point solutions that we have considered in this particular example, and you know that the corner points are the corner point solutions that we obtain here, A, B, C, D, O. So they were all enumerated as 0, 0, 0, 6, 2, 6, 4, 3, and 4, 0. Okay, so now if you look at the other corner points of this graph, so one of the corner points is 0, 9, which is of course not a feasible solution. Then one of the corner points here is 6, 0, which is also not a feasible solution. And if you look at this corner point, this is basically 4, 6, which is also not a feasible point. So there are some corner points which are not feasible. There are some corner points which are feasible. So our concentration is only on those points which are basically the feasible points. Okay. So what happens basically in the simplex method, we start with one of the corner points, and usually that corner point is the point 0, 0. So in many cases, like here 0, 0 is a part of your feasible region, but in some cases 0, 0 is not part of the feasible region. So we extend the problem by the introduction of some special type of variables which we call as artificial variables to include this origin as part of your feasible region, and then we can start from the iteration. So as you can see that this point is our starting point, and there is always an optimality check which is performed for every corner point solution of the problem, which is generated in the process, including the initial one. And if the optimality test or check tells us that the optimal solution of the problem has been obtained, we stop, or there is some other related information like the case of unbounded solution. Okay, so but if the optimality test tells us that the solution can further be improved, so we have to carry out the iterations of the simplex method. And the iterations of the simplex method moves you from one corner point to another corner point, but only to an adjacent corner point, because it moves along the edges of the or the boundaries of the feasible region. So as you can see here, we have this point 0, 0, and corresponding to this point, the two adjacent corner points are this point D. This point D means it is the point 4, this is I think 4, 6. Sorry, this point D is 4, 3. Okay, and the other corner point adjacent to this point is point A, which is basically 0, 6. So you can move either to this direction or you can move either to this direction. Both the directions you can improve the solution, because in this direction x1 will increase and in this direction x2 will increase, and depending on which is going to bring more change in the objective function value as far as the changes in x1 and x2 are considered, we will choose the direction of movement. So we will move from 0 to D or 0 to A, depending on which gives you the most possible increase in the objective function value corresponding to 1 unit change in both x1 and x2. So this way, I mean, like, so in this case, as you can see that the more increase in x2 will bring more changes in the profit, because the coefficient of x2 is higher than the coefficient of x1. So if you bring 1 unit change in x1, the profit will increase by 3, but if you change 1 unit in x2, then the profit will increase by 5. So here you can increase x2 by 6, so you can increase your profit by 30 units, while you can here at most go up to 4, and 4 into 3 is 12. So obviously the better direction of movement will be from O to A. So this simplex method always works on this principle: start with the corner point solution, test for an optimality. Okay, if the optimality test is satisfied, you stop there. If it is not satisfied, then you have to choose the direction of movement, and that direction of movement depends on the steepest rise or steepest decline in the objective function value corresponding to the given choices. So here you can see that we have moved from O to A. So this is like the path that is being chosen by simplex method starts with O, then it moves to A. Now, once it moves to A, again the optimality check will be performed. If the optimality check is satisfied, because in this case we know that the optimal solution is at B, so obviously the optimality check will not be satisfied here. Okay, so again that means we have to move further. But in this case, the only adjacent corner point to A is the point B. So there is no choice. That means choosing among the directions of movement. So here is only one direction of movement possible. So we move in this direction, and we move in this direction, and we go to the point number B. And when we go to the point number B, so we get another corner point solution of the linear programming problem. So like the graphical method, in the graphical case, we enumerate all points before we evaluate the objective function value. In simplex method, all the points are not evaluated before the iterations. The points are evaluated iteration by iteration. So whichever point comes in the path of the simplex method, to search for an optimal solution, only that point will be evaluated and rest of the points will remain unevaluated. So that means there is no need to evaluate all the corner point solutions in the simplex method before we start the iterations. So now in this case, as you can see that the optimal has been identified at the point number B. That is the best possible solution of the linear programming problem. Okay, so the iterations of the simplex method will stop at this corner point solution, which is called as the basic feasible solution in algebraic terminology. And this basic feasible solution is an optimal solution of the problem. So you can see that if you solve this problem using simplex method, this is the initial iteration where you have the initial solution feed it to the simplex algorithm. Then it generates this iteration where the corner point A is generated, and then the next iteration will generate the corner point B, which will satisfy the optimality test, and hence the process will be terminated here. Otherwise, if it is not satisfied here, it will move to the next adjacent corner point, which is the point C. Then it will move to the next adjacent point, that is the corner point D, and in the due course it will find the optimal value of the objective function at one of these corner points. So this is the idea, like with the help of which the simplex method works in an algebraic way. Okay, so now since there is not much time left, so obviously I planned initially the applications, transportation problem and assignment problem also here, but the time does not permit me, so I stop here. So any questions, most welcome. Shall I stop sharing?
Yes,
sir.
sir.
Yes, sir.
As you wish.
So if there are any questions, I would be very happy to take up them.
Sir, actually now our students are interested in this optimizational research, basically in research work. So basically few are asking about your email ID so that they can ask you the questions related to the research in optimization field.
No problems. My email ID is with Professor Neetu Gupta ji.
Sure,
So yeah, you can take the email ID from her and pass it on to the students. So whosoever is interested in, making a query or any related questions, I would be happy to answer them.
yes, sir. So students can take directly the email ID from.
Yes, sir. I will share. I will share with the students.
Yeah. So Neetu ji, please share the email ID with the students if they are interested in contacting me for any of the queries or questions related to optimization, research in optimization. I will be very happy to
Definitely, sir.
respond to the best of my capabilities. Okay.
Yeah. Yeah. Sir.
Thank you, sir. Thank you so much. We are grateful for the time and efforts you took to share your expertise and enlightening us with the knowledge. It was a pleasure listening to you. Thank you so much, sir. Sir, you have proven the quote given by Marcin, the best teacher is not the one who knows most, but the one who is the most capable of reducing knowledge to the simple compound of a obvious and wonderful thing. Thank you, sir. Thank you so much, sir.
Thank you to all of you for giving me an opportunity to speak in this program. So great effort by the organizers to organize this event for the UG and the PG students. So thank you to all of you for a patient hearing, especially the students. So can I leave now?
Thank you so much, sir.
Yeah.
Okay, sir.
Okay, ma'am. Thank you.
Excuse me, sir, if we can have a group photograph with you for our future reference.
Sure.
Yeah.
I'll just switch on the video.
G. Manu ma'am? Okay, I can take. Yes, sir. Thank you very much, sir.
Okay. So I now leave this meeting.
Yes, sir. It's your wish.
Okay, sir.
Okay, because I have some classes, and the administrative work to take up. So I take your leave now. Okay, thank you very much once again.
Thank you very much, sir.
Okay.
Thank you, sir.
Now result announcement by the coordinators. Now we will declare the result of various events held yesterday. Now I invite the Dr. Reena Garg to declare the result of national level.
December 21st, the Department of and coordinators for the I would like to thanks to the student coordinators, Mr. Rohit, Ms. Reshu, and Ms. Anjali for doing this commendable job to run this program successfully. The result is finalized by composition, relevance to the theme, creativity, and presentation of the poster. The winners of the competition are Yogita Yadav, a student of MSc Mathematics from Hindu College, University of Delhi, got the first position. Divya Babbar and Simran of MSc Mathematics, third semester from JC Bose University of Science and Technology, IMCA Faridabad, got the second position. JC Bose University of Science and Technology, and Prachi, MSc Mathematics, 5-year integrated course, fifth semester from Maharishi Dyanand University, Rohtak, got the third position. Thank you.
Minu ma'am, you are not audible. I think we can invite the next presenter. I think Mr. Abhishek. Abhishek, I think you can share your PPT and you can announce the results.
Is my screen visible, Dr. Suraj? Hello.
Abhishek, you are audible enough.
Is my screen visible?
Yes, Abhishek.
Okay. Good morning, everyone. I am here to present results for PowerPoint presentation. On December 22nd, 2021, the Department of Mathematics, JC Bose University of Science and Technology, YMCA Faridabad, Haryana, organized the national level competition for PowerPoint presentation, sponsored by Haryana State Council for Science, Innovation and Technology, to celebrate 134th birth anniversary of Srinivasa Ramanujan on Mathematics Day. In PowerPoint presentation competition, there were 43 participants from various universities and colleges. The participants were from Maharishi Dayanand University Rohtak, Hindu Girls College Sonipat, JC Bose University of Science and Technology, YMCA Faridabad, Government College Matan Hill Jhajjar, and Saraswati Mahila Vidyalaya. Participants were both from undergraduation and post-graduation. There were 4 themes provided to the participants for the same, that includes mathematics for a better world, mathematics and ancient history, mathematics, a language of universe, and world without zero. Each participant had to present their PPT in the time period of 8 to 10 minutes only. The results were announced by the judges on the basis of following criteria: originality, creativity, organization of content, oral presentation, clarity, artwork, and animation. The winner of the competitions were: first position goes to Ms. Swati Singh and Ms. Srishti Bharadwaj. Second position, Ms. Kumkum and Ms. Divya. And the third position goes to Mr. Lokesh Kaushik. Thank you. Okay, over to you, Dr. Suraj. Over to you, Dr. Suraj.
Yes, thank you, Abhishek. Okay, so now we can invite Dr. Arpita Chatterjee. Ma'am, you can declare the results of your respective competition. So let me share my screen, ma'am.
Okay, thank you, Dr. Suraj.
Just give me a moment, ma'am.
Okay.
Yes, ma'am. I think my screen is visible now.
Yes, your screen is visible. So, good morning, everyone. So, we are studying in our debate competition. Nearly 50 participants, they have registered from different branches of JC Bose University, including BTech, BSc, and MSc. These branches are from Delhi University, from MDU Rohtak, and from Jamia Millia Islamia University, of which 24 has joined the competition. The themes for the competition were: is mathematics invented or discovered? Does mathematics reveal reality? And the third theme was, should laptop be allowed in classroom? So most of the students, they were spoken about these third topic. The participants, they have to speak either in support or in against of their chosen topic within a time limit of 3 to 5 minutes. So they have options to present their topic either in Hindi or in English, but most of them, they have opted for English. So for this competition, myself, Dr. Arpita Chatterjee and Dr. Pooja Gupta, we were the judges, and Ms. Muskan from MSc Mathematics was the coordinator for the competition. So the winners for the competition are: first prize goes to Hardik Mehta. He is from BTech Computer Engineering from JC Bose University. Second prize goes to Khushi Gupta, BTech Computer Engineering, JC Bose University, and Mansi, who is from BTech Robotics, JC Bose University. And third prize goes to Mohit Tanbar, who is a student of MSc Mathematics, Delhi University. So this is the result. Thank you. Thank you all. Suraj.
Okay, thank you, ma'am. I think, Minu ma'am, you can conclude the valedictory now.
Thank you, sir. Now I request you all to please turn on your camera to capture the memory of this event. Thank you so much. I thank you, VC sir, Vice Chancellor sir, Shri Raj Nehru sir, worthy Registrar sir, Dr. Sunil Kumar Garg, the eminent speaker, Professor Pankaj Gupta sir, and Professor H.C. Taneja sir, and the chairperson of our department, Professor Neetu Gupta, for gracing the occasion. Now I also thank to all the participants in this two-day program on National Mathematics Day. I am really excited to express the closing thanks of the function. I congratulate all the faculty members for organizing this program. Thank you, everyone, once again. Thank you so much, everyone.
Okay, thank you, everyone. That's it from our side. So all can leave the meeting. Thank you, everyone.